Good afternoon. My name is Vladimir Ivanov, and now I will demonstrate the technology developed as part of my doctoral research for authentication of fingerprint sensors, which to our best knowledge is the first and still the only such technology. Using biometric information for verifying the identity of a person, that is, for authenticating them to systems, provides convenience. One of the most widely used biometrics is fingerprints. Because they are highly distinct, develop early in life, and are relatively permanent over time. Today, the technology for automated authentication using fingerprints is mature, and low-cost and small-sized implementations are readily available. However, fingerprints, and generally most biometrics, have a low degree of secrecy, are difficult to change, and cannot be revoked. Thus, their compromise may lead to more serious consequences than, for example, a compromise of a password. Furthermore, the widespread use of biometric technologies are set to make the biometric information essentially publicly available, with the face photos being public even today. Phones with fingerprint sensors have become widely used, starting with Fujitsu's Rexa and Eros to Motorola's Atrix 4G, to Apple's iPhone 5S, to Samsung's Galaxy S5, to name a few, and it has been shown that their fingerprint authentication can be easily spoofed. When authenticating to mobile devices, such as laptops or phones, security problems may arise because this authentication typically takes place in unsupervised environments, for example at home. Since mobile devices are easily stolen, an attacker with physical access to them can launch a powerful attack by manipulating the data acquired and transmitted by the biometric sensor. Thus, possible and increasingly feasible attacks are malicious replacement of the authentic sensor, the one that is legitimately connected to the device, and replay of a stolen image of the authentic fingerprint as output of the fingerprint sensor. Such attacks can be countered by verifying the authenticity of the sensor which acquired a particular fingerprint image, that is, for authenticating the sensor itself. It turns out that fingerprint sensors can be distinguished based on their pattern, which we call scanner pattern. It is caused by imperfections of the image acquisition process and gets embedded into the pixel values of every image the sensor acquires. Although the scanner pattern is imperceptible by the naked eye, it is strong enough to be extracted from an image. It is also sufficiently persistent, unalterable, and unique, even among sensors of exactly the same technology, manufacturer, and model. Extracting and comparing the scanner pattern with an already registered pattern verifies the authenticity of the sensor in a process which we call sensor authentication. Let's say this is our authentic sensor, and this is an image acquired by it. We extract the scanner pattern from the image and store it into the system for future comparison. This is the sensor enrollment. Now comes the sensor verification. If again the same sensor acquires another image, we again extract a scanner pattern from it and compare this pattern with the pattern already stored in the system. Since this is the same sensor as before, their patterns are sufficiently similar, and the system recognizes the sensor as being the authentic one. The determination is based not on metadata in the image, but on processing and analyzing its pixel values. Now, if another sensor, even if exactly the same type, manufacturer, and model, acquires an image from which a scanner pattern gets extracted and compared with the pattern already stored, the two scanner patterns are different, and the system recognizes the sensor as being an unauthentic one. In this way, the scanner pattern can enhance the security of a biometric system by authenticating the sensor and detecting attacks on it, such as detecting an image containing the fingerprint pattern of the legitimate user and acquired by the authentic fingerprint sensor, replaced by another image that may still contain the fingerprint pattern of the legitimate user, but has been acquired by another, unauthentic fingerprint sensor. We have developed the technology for and tested on widely used general-purpose, commercial, off-the-shelf capacitive fingerprint sensors of both area and swipe types, as mobile devices are most likely to be equipped only with such components. The technology is extremely accurate, yet very simple, computationally efficient, and fast. The computational efficiency and speed are very important also because the sensor authentication is only one part of the authentication process, and therefore the time it adds has to be very little. This is also extremely important if it becomes used for sensor identification. And all this is even for sensors of exactly the same acquisition technology, manufacturer, and model. Furthermore, it needs only a single image to unroll the sensor and a single image to verify it. The technology is also robust in a wide range of conditions. The pattern of each finger is distinct not only among different individuals, but even among the fingers of each individual and of each hand. The pairs of fingers of one person also have different patterns. Our technology works even when one finger is used to unroll the sensor and another finger to verify it. It is also robust when the fingertip is pressed softer or harder on the sensor, when the finger skin is moist, and for different temperatures of the fingerprint sensor. The technology also does not require any hardware modifications and can be added as a software add-on to already manufactured systems. Because of its great simplicity, it can also be implemented entirely or partially in hardware, when available. We have also protected it and implemented in software for both area and swap fingerprint sensors and successfully demonstrated it at trade shows. I will now demonstrate the authentication of area fingerprint sensors. Here are 24 area sensor modules, each one containing a TCS1 area sensor, originally developed by UPEC and now part of the product line of Crossmatch Technologies. The TCS1 area sensor is the only capacitive and generally silicon fingerprint sensor that is FIPS 201 certified, which means that the sensor meets the image quality specifications of FBI's integrated automated fingerprint identification systems. In area fingerprint sensors, also called touch sensors, the image is acquired when the fingertip is placed fixed on the sensor. The modules are connected via development kit to the computer over USB. I will now randomly choose one sensor. This will be our authentic sensor. Its number is U116. I will connect the sensor and enroll it by acquiring an image with a fingerprint. I will use an arbitrary finger for this, for example, my right ring finger. The sensor is now enrolled. The images are scrambled when displayed in order to conceal my fingerprints. This is still the same, the authentic sensor. Now I will verify this by acquiring another image. For our technology, the fingertip used for the image acquisition does not matter. So I will use another arbitrary finger, for example my left middle finger. I reset the image, place my finger, and verify the sensor. The verification process produces a score from about 0 to 1. The decision threshold for area sensors is approximately 0.36. So if the score is above this threshold, the result is sensor match. That is, this is the authentic sensor. If the score is below this threshold, the result is sensor non-match, which means that this is an unauthentic sensor. Now the score is 0.94, which is well above the decision threshold, so the result is sensor match, and the authenticity of the sensor is confirmed. Now I will check the sensor using my right index finger. The score is 0.92, so again we have sensor match. The signal processing is symmetric, so the image for the sensor verification is processed in the same way as the image for the sensor enrollment. I now remove the authentic sensor and place it here. I choose randomly another sensor. I will use my right ring finger, the finger I used to enroll the authentic sensor. The score is 0.06, which is well below the decision threshold, so the result is sensor non-match. That is, this is an unauthentic sensor indeed. So the finger was the same, my right ring finger, but the sensor was different from the authentic sensor. I will repeat this with another finger. This is my right index finger. The score is 0.01 and the result is sensor non-match. With my left middle finger, the score is 0.07 and the result is sensor non-match again. I now replace the unauthentic sensor by another sensor, again chosen at random. This time I will start with an arbitrary finger, let's say my left ring finger. The score is 0.02 and the result is sensor non-match. With my right ring finger, the finger I used to enroll the sensor, the score is 0.08 and the result is sensor non-match again. I will now connect back the authentic sensor. And use an arbitrary finger different from my right ring finger. With my left index, the score is 0.92. So it's sensor match, and indeed this is the authentic sensor. With my right ring, the finger I used to enroll the sensor, the score is again 0.92 and the result is sensor match. Now let's check with my left little finger. The score is 0.93 and the result is sensor match again. In addition to working with images containing patterns of different fingers, the technology works properly even when not a fingertip, but another body part is applied to the sensor, for example a palm, because it inherently does not rely on specific characteristics of the fingerprint pattern. Now I apply my palm and the result is again sensor match because the score is 0.89. Making the technology robust in a wide range of conditions was a very important objective because this can ensure its adoption. Pressing hard the finger onto the sensor changes the fingerprint signal in the image in a nonlinear way and could result in problems for verifying the fingerprint. We took measures to counter this effect, so it is not a problem for the sensor verification. Our authentic sensor is still connected. I will press hard my right middle finger. The score is 0.92 and the result is sensor match. I will also use my thumb finger. Thumbs typically have wider ridges and valleys than the other fingers, and more importantly, they're stronger and can press harder. I will also stand up to put my weight on the pressing thumb. With my right thumb finger, the score is 0.88 and the result is sensor match. With my left thumb finger, again pressing hard, the score is 0.82 and the result is sensor match again. Notice how dark these images are in comparison with the previous images. Now I will test this with an unauthentic sensor. I remove the authentic sensor and choose another one. I will press hard my right middle finger again. The score is 0.02 and the result is sensor non-match. With my right thumb finger pressing hard, the score is minus 0.03 and the result is sensor non-match again. Finally, with my left thumb again pressing hard, the score is minus 0.02 and the result is sensor non-match again. Moisture on the fingertip from water or from another liquid creates problems for many fingerprint verification algorithms, but not for the sensor verification because it is designed to be robust against that. Now I again connect the authentic sensor. This is a skin moisture sensor. It measures the skin moisture of my left ring finger. Its moisture level is 63, which is in the normal range. I will put some water on my finger. And again measure its moisture level. Its moisture level is 92. Then I verify the sensor. Now the score is 0.90 and the result is sensor match. Notice how dark this image is. I will do this again with my right little finger. I'll moisten it. Measure its moisture level, again 92, and verify the sensor. The score is now 0.85 and the result is sensor match again. I will test this with an unauthentic sensor. I remove the authentic sensor and choose an unauthentic sensor, again at random. I again moisten my right little finger. .92. Let's moisten it more. Again 92. Okay. and I verified the sensor. The score is 0.07 and the result is sensor non-match. Now let's do this with my left index finger. (93). The score is 0.09 and the result is sensor non-match. Again, notice how dark these images are. As with most semiconductor devices, the performance of the capacitive fingerprint sensors is temperature dependent. Knowing this, we developed the technology specifically to work in a range of temperatures and tested it on images acquired at temperatures measured on the surface of the sensor from about 5 degrees Celsius to about 40 degrees Celsius. We can demonstrate this upon request. Finally, the processing is scalable and can provide arbitrarily high accuracy as more pixels are used, at the cost of linearly increasing computational time. This current demo implementation, the sensor enrollment and no sensor verifications, process only about 20% of the pixels in each image. Next, I will demonstrate the authentication of swipe fingerprint sensors. Here are 24 swipe sensor modules, each one containing a TCS 4K swipe sensor, originally developed by UPEC and now part of the product line of Crossmatch Technologies. In swipe fingerprint sensors, also called slide sensors, the image is acquired when the fingertip is swiped over the sensor. The modules are connected via a development kit to the computer over a USB. I will now randomly choose one sensor. This will be our authentic sensor. Its number is U510. I will connect the sensor and enroll it by acquiring an image with a fingerprint. I will use an arbitrary finger for this. For example, my left index finger. The sensor is now enrolled. The images are scrambled when displayed in order to conceal my fingerprint. This is still the same, the authentic sensor. Now, I will verify this by acquiring another image. For our technology, the fingertip used for the image acquisition does not matter, so I will use another finger, for example my right middle finger. I reset the old image and verify the sensor. The sensor verification produces a score from about 0 to 1. The decision threshold for swipe sensors is approximately 0.55. So, if the score is above this threshold, the result is sensor match, meaning that this is the authentic sensor. If the score is below this threshold, the result is sensor non-match. So this is another unauthentic sensor. Now, the score is 0.89, which is well above the decision threshold. So the result is sensor match, and the authenticity of the sensor is confirmed. I will also check the sensor using my left little finger. The score is 0.87 and we again have a sensor match. The signal processing is symmetric, so the image for the sensor verification is processed in the same way as the image for the sensor enrollment. I now remove the authentic sensor and place it here. Then I take another sensor, again at random, I will use my left index finger the finger I used to enroll the authentic sensor. The score is 0.37, which is below the decision threshold. So the result is sensor non-match. That is, this is an unauthentic sensor indeed. So the finger was the same, my left index finger, but the sensor was different from the authentic sensor. I will repeat this with another finger. With my right middle finger, the score is 0.38, and we again have a sensor non-match. I will now connect back the authentic sensor. And use a different finger from my left index finger. Now with my left middle finger, the score is 0.95, and we have sensor match. Indeed, because this is the authentic sensor. Now with my left index finger, the finger I used to enroll the sensor, the score is 0.96, and we again have a sensor match. Now let's check with my right ring finger. The score is 0.88, and the result is again sensor match. In addition to working with images containing patterns of different fingers, the technology works properly even when not a fingertip, but another body part is applied to the sensor, because it inherently does not rely on specific characteristics of the fingerprint pattern. Now I swipe the side of my hand, and the result is again sensor match, because the score is 0.93. I now again replace the authentic sensor by another sensor. Again, chosen at random. This time I will start with an arbitrary finger. Let's say my left little finger. The score is 0.15, and we have sensor non-match. With my left index finger, the finger that I used to enroll the authentic sensor, the score is 0.31, and we have again sensor non-match. Finally, I replace the unauthentic sensor by yet another one, another unauthentic sensor. With my right ring finger, the score is 0.24, and we have sensor non-match. Now with my left middle finger, the score is 0.26, and we again have sensor non-match. Moisture on the fingertip from water or from another liquid often creates problems for the fingerprint verification algorithms using images acquired by swipe sensors. But the sensor verification is designed to be robust in such conditions. I will connect back the authentic sensor. This is a skin moisture sensor. Now it measures the skin moisture level of my right little finger. Its moisture level is 54, which is in the middle of the normal range. I will now put water on this finger. And again measure its moisture level. Moisture level is 99, which is the maximum on this indicator. With this finger, I will verify the sensor. The score is 0.88, and we again have sensor match. Notice how dark this image is in comparison with the previous images. I will repeat this with my left thumb finger. Its moisture level is 99, again the maximum. And the score is again 0.88. So we again have sensor match. Now I will test this with an unauthentic sensor. I remove the authentic sensor and choose another one. I again moisten my left thumb finger. Again 99. And verify the sensor. The score is 0.42, and we have a sensor non-match because this is an unauthentic sensor. And finally, let's check with my right little finger. Again moistened with moisture level 99. The score is 0.46, and we again have a sensor non-match. The demonstrated technology, based on extracting and matching the scanner pattern, can be used to authenticate the sensor and detect attacks on it. For example, to detect a malicious sensor replacement or replay of a stolen image of the authentic fingerprint at the output of the sensor. It can thus enhance the security of a biometric system, such as to detect an image containing the fingerprint pattern of the legitimate user and acquired by the authentic fingerprint sensor, replaced by another image that may still contain the fingerprint pattern of the legitimate user, but has been acquired by another, unauthentic fingerprint sensor. Combining the biometric authentication with the sensor authentication leads to a two-part authentication, which we call Bipartite authentication, that verifies the authenticity of both the user and the fingerprint sensor. It consists of bipartite enrollment, which is enrolling both the fingerprint and the sensor, and verifying that both the fingerprint and the sensor are authentic. As the bipartite authentication verifies both who the user is, that is, their fingerprint, and what the user has, it binds the user and their device. The difference with the other two-factor authentications is that here both factors are contained in and extracted from the same image. It can also be used for authentication or identification of devices such as phones, tablets, and laptops that are equipped with fingerprint sensors. Thus, it can use the sensor to authenticate the device instead of sending the biometric information over the network in order to authenticate the user. In this way, the biometric information is locked in the device and never leaves it, hence allowing anonymity and privacy. Its possible areas of application include mobile wallets, such as Pay by Finger, and banking applications, access to healthcare and medical records, contextual authentication or user rights, for example, as part of the identity management without aid and independently from the telecom operator to verify from which device the user logs in, and also for asset management. Thank you.